Welcome to this course of Data Structures and Algorithm, and we are teaching this course at the Department of Computer and Software Engineering. At Information Technology University, and this course and lecture is specifically meant for the BS program, undergrad program Computer Engineering, with the course code CE200T. And I'm your instructor, Dr. Tahira Mehboob, and you can find my contact address, email address on this first slide. So let us continue with the lecture. And today's lecture, we are going to study one of the shortest path algorithm, and we are to find the shortest path on a graph, and that graph can be a directed graph, it could be an undirected graph. So this algorithm works for both directed graph and undirected graph, and the target is to find a shortest path from any given vertex to another within a connected graph. So Dijkstra's algorithm is a popular algorithm for solving many single source shortest path problems, having non-negative edge weights in the graphs. That is, we have to find the shortest distance between two vertices on a graph. And the idea was conceived by a Dutch scientist named Dijkstra in 1956. So the algorithm maintains a set of vertices where we can see in a graph. This is a graph, example of a graph, which is a directed graph because we have direction from source vertex to the destination vertex. So the circles that we are representing here, they are basically your vertices, and the line that is connecting these two vertices, we refer to them as the edge. So the algorithm works by maintaining a set of visited vertices and a set of unvisited vertices. It starts at the source vertex and then iteratively selects the unvisited vertices with the smallest tentative distance from the source. Once it has visited one of the nodes, for example from 1 to 3, it has selected the vertex, it then visits the neighbors or adjacent vertices of this vertex and updates their tentative distances. If a shorter path is found. This process continues until the vertex, all of the vertices have been visited. So in this algorithm, what we do is we maintain two sets for the visited and the unvisited vertex. Start from the source and then select the vertices that give us the shortest distance between those two vertices. And once a vertex has been visited, if there is another path to an already visited vertex, and if it is smaller than the existing path, then it updates the existing distance from that source vertex to the destination vertex. So what we are doing is we are finding the shortest path from source node to the vertex, and we can start from any node as the source, and it is essentially a minimization problem, an optimization problem. And such kind of minimization problems, they can be solved using a greedy approach. And the algorithm can work on both directed as well as undirected graph. As I mentioned, we have these circular nodes, they are the vertices, and the line that connects these two vertices is the edge. And if we have an arrowhead on the edges, we refer to them as the directed graph, otherwise it is the undirected graph. So we use the greedy approach in the Dijkstra's algorithm to find the minimum path from any source to the destination vertex or the selected vertex where we want to reach. What is the greedy approach? So the greedy approach is solved, a problem is solved in stages, where we consider one step at a time, taking one input at a time to get to the optimal path. And in the Dijkstra's algorithm, we have a predefined procedure to get to an optimal solution. For example, if you're to visit all the nodes starting from vertex 1, where we have total 6 vertices, and we have to reach all of these vertices one by one. So in the first iteration, we will select the vertex which gives us the minimum path. So from node 1, we have two paths. Either we can move towards 2 or we could move towards 3. And in these two, option 1 and option 2, option number 1 gives us a shorter distance, that is 2 compared to 4, which is distance between 1 and 3. So your algorithm will choose the shortest path. In this case, the path from 1 to 2 is shorter than path from 1 to 3. So we select this path. So initially we have visited the vertex 1. Then we have visited the vertex 2. We have selected that vertex, and now we will consider all the paths that we are going from vertex 2 to the next nodes, to the neighboring nodes or the adjacent nodes. Those nodes that are connected to the vertex 2. So in this case, we can see that 3 and 4 are connected to vertex 2, and we estimate the cumulative path. So if we are to go from 1 to 2, we have already gone there, and from 2 we can go either at 3 or we could go at 4. So the distance required to reach 3 is 2 plus 1, which is 3, and distance required to go from 2 to 7 or 1 to 4, this path, it is 7 plus 2, which is 9. So in the two paths that we have, the distance estimation, 3 gives us a shorter path. So in this case, your vertex 3 is selected. We have to calculate the cumulative path. So first we select 1, then 2, and then 3. Here we have estimated the path to be 3, and in this case it is 9. So we select 3, and only one edge is going out of the tree. So we select the next node, which is 5, and the estimation is 3 plus 3 is 6. So the distance required to reach from 1 to 5 is 6 using the shortest path. From 5 again we have two options. Either we can move in this direction, or we could move in this direction. Out of the two, we estimate that reaching from 5 to 4, the cumulative path becomes 8. Before it was 9, now it is updated to 8. And reaching from 5 to 6, starting at point 1, at vertex 1, now we have estimation is 11. So among these two, 8 and 11, 4 is selected. From 4, we have only one way, that is towards 6, and 8 plus 1, now before it was 11, now it is estimated to be 9. So the shortest distance to reach from 1 to node 6 is 9. Shortest distance to reach from 1 to 2 is 2. Shortest distance to reach from 1 to 3 is 3. 2 plus 1. The shortest distance to reach from 1 to 4 is, rather we first visit 5, so 1 to 5 is 6. 3 plus 3, 6. Shortest distance to reach from 1 to 4 is 8. And the shortest distance to reach from 1 to 6 is estimated to be 9. So this is essentially how our algorithm operates. Here we have an example to start off with the basic understanding of our Dijkstra's algorithm. We know that it's a single source path, always starting from a single node, and we select a vertex with the shortest path. We will have multiple paths, but we will choose that vertex which gives us the minimum cumulative path. And if we have already calculated the shortest path before, and we now in the next iteration have a shorter path compared to the previous path available, we will update the path using the relaxation condition. So I will explain this relaxation condition, but first we have an example here. We have 3 vertices, T, U and V, and we want to reach from T to V. So T is our source vertex, and the distance from T to U is 2. But at this point, we do not have any direct path from T to V. So we will allocate an infinity to the distance from T to V as infinity, because it is not directly reachable, but the distance from T to U is 2. So once we have reached from T to U, now our vertex V is visible, so we can calculate the cost from going from U to V. The cost is 4. So the total distance to reach from T to V will be the distance that we have here, that is 2, plus the distance that we have here is 4, which is the cost from going from U to V. It is 6. So we can only update the distance value if we have a edge between the vertices. So if the distance du the relaxation condition. If the distance du we have directly connected, so we know the distance of d to u, which is 2, plus cost of going from u to v. If we know that, if it is less than the distance from d to v, okay, so we are here, we can only see here, which is the du plus the cost from going from u to v, which is 4. Cost of going from u to v, if it is less than the distance directly from d to v. So if we see from this point, the distance dv is infinity because it is not visible. First we have to go to this vertex and then we can reach the next vertex. So which is less than infinity, which is, this is dv is infinity, and the cost that we calculated here is 2 plus 4, which is less than infinity. So now we can update dv as the cost from going from d to u, which is 2, and the distance du and the cost from going from u to v, 2 plus 4. So that this dv is updated from infinity to 6. We can have this relaxation condition. So Dijkstra's algorithm, it is based on this relaxation condition. Okay, if we start here, we can see in this example, this is your starting vertex, and we have to estimate the distances from vertex 1 to all other vertices. So initially at the starting stage, 1 is directly connected to 2, so the distance is 2. 1 is directly connected to vertex 3, so the distance is 4. However, at this stage, in the initial stage, we do not know the distance from going from 1 to 4, or going from 1 to 5, or going from 1 to 6. So we will allocate an infinity distance to these 3 nodes, because at the first iteration we are only at the first stage or the first node. So source node, we will always allocate distance going from 1 to 1 will always be 0. So going from here to here will always be 0. Okay, now from among these 2 distances, which is a shorter path, we will see select 2. 1 is already selected as the source. Now 2 is selected and the distance is 2. And then from 2 we can go either at 3 or we could go at 4. So if we go at 3, we will sum it up, and then initially it was 4, but now if we go to 3 via 2, vertex 2, the distance becomes 3 instead of directly going, that is 4. So the distance was previously 4, but now it has updated to 3. Now when we are at 3 is selected, and then we have only one path that leads to vertex 5, and the distance from between the cost going from 3 to 5 is 3. So 3 plus 3 becomes, initially it was infinity, but now it has been estimated as 6. So this is only one path. So now 5 is selected as your next node. From 5 we have 2 paths. Either we can move towards the node 6 or we could move to the node 9, node 4. So in this case, if we move towards node 4, the distance becomes, initially we can see it was 9. If we go from 2 to 4 via 2, it was 9, but now if we go from 5, it has been updated to 6 plus 2 equals 8. So now your vertex 4 is selected. So 4 is selected now, and we have only one path that we can move in this direction. So in this case, we can, if we go from 5, 6 plus 5 is 11. Initially it was infinity in the previous stage, and now it has become 11 because we have a path available from going to 5, and among 11 or 8 we have selected 8. So 4 is selected, and if we go from 4 to 6 vertex, so it was 8. Now add this cost, that is 1. So 8 plus 1, it is, initially from going from here it was 11, but now it is updated to 9. So the distance, the path that we are going to take is from here to here and then here. This is the aggregate, the final path, which is the shortest path, or we could say it is, the path is 1 2 3, then 5, then 4, then 6. We need to select the shortest path from the adjacent vertices. So going to vertex 2 is, distance of V is 2. From starting vertex is vertex 1. If we want to go to 3, it is 3, which we have estimated. If we want to go to 4, it is estimated to be 8, as we did here. Going to 5, it is estimated to be 6, and going to vertex 6, which is the final longest path, which is 9. So this is your Dijkstra's algorithm to calculate the shortest path.